So we are at the fourth episode of Topology from the series Gravitation. We are going to talk about homeomorphism. This is where all the cool stuff happens. I'm sure you are familiar with the donut and mug story from the topological aspect. These two things are same. It means with a couple of homomorphism, which I'm going to say what it is, you can transform a donut to a mug, or as they say, for a topologist, a donut and a mug are the same thing. So we have the definition of homeomorphism right here. F, X, and Y are topological spaces. A homomorphism from X to Y is a bijective map phi from X to Y such that both phi and phi inverse are continuous. So one thing that you may have noticed is that we mentioned that both phi and phi inverse should be continuous. So you may think that our function is bijective, and if the phi itself is continuous, then the inverse should also be continuous, but that's actually not true because we have a counter example. Take these interval and let's take it to the unit circle. So these will go here and bend it so that these goes there. And you can actually, this is not a closed interval. It is open from one side. As you can see, this thing right here is continuous, but the inverse will not be continuous because of the region here. One of them will be one of the points from here will go here and the other will go the other way of our line. So if phi is continuous and bijective, that does not mean that the phi inverse should be continuous. So you need to check that both phi and phi inverse are continuous. Another thing about homomorphic spaces, by the way, we call two spaces homomorphic if we have this homomorphism between them. The homomorphic relation is actually an equivalence relation. If you don't know what equivalence relation is, it's a relation, for example, let's denote the relation with this. We say we have an equivalence relation if A and B have a relation, then B and A have a relation. If A and B and C and D have a relation, B and C have a relation, then A and C have a relation, and A has a relation with itself. This is the three condition to have a equivalence relation, and you can check that homomorphic gives equivalence relation. And then we have an exercise. If F is a bijective map, then F is a homomorphism if and only if the F of that curly T, which we discussed, which is the topology of X, the F of that set gives you the topology for the topology of X2. So I think this is a good exercise. You can think about it, and I will tell you the solution in just a sec. So let's first do this way. Um, if if f is a homeomorphism, then obviously it takes the open sets to open sets, and the inverse of it also does the same thing. So this is the collection of all open sets, and since it's a bijective map, then it gives all of T2. And the other way is pretty similar. You can do it on your own. Now we have a definition. If T1 is a subset of T2, then we say that T1 is coarser than T2. And if T2 is a subset of T1, then we say T1 is finer than T2. One thing you may notice, you may think that this selecting of names, I mean coarser and finer, are really are working in the opposite way, but that's not true. Because if T1 is a subset of T2, then this means that T2 has more open sets. So the T1 is coarser. And if T2 is a subset of T1, then this means that T1 has more open sets. Okay, so the space is made out of more open sets. So I have an example right here. Take T1 as this set and T2 as this one. As you can see, T2 is made out of more open sets, so we say that T2 is finer than T1. The understanding of this is pretty trivial. You should just remember why we name them like this. Then there is a homeomorphism between the n-dimensional Euclidean space and the unit ball, which is also in dimension n. This is, by the way, defined as the norm of x being less than 1. So this is, so the definition of a ball is right here. Now, with these two functions, we can see that these two spaces are actually equal with respect to homomorphism. So we say that they are homomorphic to each other. And there is a conclusion from this. As you know, this thing right here has a bound, which is 1. But this space does not have any bound on it. So the conclusion will be that boundedness is not a topological property. And at least we have the definition of local homomorphism, which is just the definition of homomorphism, but in a local space. And that's it.